In the next 40 minutes or so, what I'd like to do is give you a bit of a whistle-stop tour of ocean acidification research, a little insight into what the problem actually is, the kind of things we've done to try and assess what the impacts are likely to be, and a little look into the future to see how the research is developing and the tools and the techniques are starting to move forward to make bigger predictions over spatial and temporal scales that are much more in line with what ocean acidification and climate change research should be doing in general. So let's start with the cause of the problem. Let's reflect on the fact that we know that we are producing a huge amount of carbon dioxide and we're putting it into the atmosphere. And it's not really the amount of CO2, or that's important in itself, but it's the rate at which we're increasing the CO2 burden in the atmosphere. We're putting CO2 into the atmosphere at a rate that's an order of magnitude faster than anything we've seen before in our planet's history. This CO2, we know, is going in primarily through the energy generation, through the burning of petroleum, coal, natural gases. But there's other factors as well, such as deforestation and cement production and other activities which are contributing to this rather alarming rise in atmospheric CO2 levels. The idea that it's going to get better, I think, has now been thoroughly debunked, and actually even under the most optimistic of predictions into the future, we're still looking at scenarios whereby we're seeing temperature rise, global average temperature rises above which we think are going to be damaging for the system. The ones in red are the very, very worrying scenarios, and rather scarily the estimates and the actual measurements at the moment do seem to be heading off that way. Let's hope that in the years we can start to move down at least to some of these less severe scenarios. However, that's the problem, the CO2 in the atmosphere. With regards to temperature, I think this was a really nice visualization of how temperature has been changing over the last 150 years or so. What you see here as this figure starts to evolve is at the early part of the 1850s, you see the temperature in the middle here. This is a seasonal cycle, and it moves in and out through decades, but in essence it's just cycling around here. As this curve moves out towards the edge, it's this increasing temperature out towards this 1.5 and 2 degrees increase in global temperatures. You can see that, particularly over the last dozen or so years, that rate at which the temperature is moving away from what we'd normally expect is accelerating. So things are getting worse, and they're getting worse very quickly. So the atmospheric CO2 creating this warming of the planet. However, the CO2 isn't staying in the atmosphere, and that is the problem associated with ocean acidification. The atmospheric CO2 actually reacts with the seawater to create a weak acid that easily disassociates. It's carbonic acid here. And carbonic acid here. And what that does is it does a number of things to the carbonate chemistry of the ocean. It increases the hydrogen ion concentration, and that is, in essence, the pH level. This is the classic side of ocean acidification and how it got its name. But there are other things as well, such as the reduction of carbonate ions, increase in bicarbonate ions. And for marine organisms and ecosystems, it's not just about the changing acidity, it's also about the host of other changes associated with this disruption of the carbonate chemistry system. Initially, we thought that the carbonate system was so robust and so big that actually it was very well buffered in the ocean. But if you reflect back to the graph I showed at the very start, it's the rate at which we're putting CO2 in. The buffer system in our oceans cannot cope with the speed, and therefore we're seeing big changes in carbonate chemistry. In the last sort of analogous event, the PETM, which occurred many thousands of years ago in geological history, A similar amount of CO2 was put up into the atmosphere as we're predicting is going to go up now. However, it went into the atmosphere over thousands of years, not over hundreds of years. And actually, the oceans were thought to be able to cope. And the changes in ocean chemistry seen during that last event are nowhere near as great as what we're predicting to change in the current situation. And it's real, it's being measured. There are a number of long-term data sets out there now that you can actually see the trend. Initially it was difficult because CO2 in the marine environment is incredibly variable. The noise around this mean is huge. And actually that's an important aspect of ocean acidification as well, that intrinsic variability. Because organisms are living in an environment where CO2 varies a lot. So whilst you might think that would make them more tolerant, what it actually does is it makes their systems more sensitive because they are used to change, they're dealing with change in CO2, so they have physiological and behavioral processes to deal with CO2. But that's normal CO2, and what we're doing is we're taking it out of that normal envelope now. A number of early studies were lots of experimental studies. We generated a huge amount of data, taking organisms, exposing them to high CO2, looking at various physiological responses. And all these data have been brought together in a number of meta-analyses. And in fact, this one was done quite a few years ago now. But some have been done more recently. They show very similar things. That as a general trend, we see marine organisms, some of their key physiological and behavioral functions are being negatively impacted by high CO2. Things like survival, just general ability to withstand exposure to prolonged CO2, prolonged exposure to CO2. Calcification, probably not a surprise given that this is the actual process which makes these calcium carbonate skeletons and shells that the organisms depend on, and it's so intrinsically linked to the carbonate chemistry of the oceans or the media in which they live. Growth, and this is soft tissue growth, so the energy able to put into growth is being reduced. Photosynthesis, less of an impact, but then again CO2 is a nutrient, so maybe it's not something we would have expected to see at least a negative impact. Possibly a positive impact, but there doesn't seem to be a positive impact on photosynthesis. So there's general trends appearing, but of course, the organism that you particularly study or you farm or you're interested in, it's not about general trends. We need to know specifics. And we also need to know how organisms are going to react within the real world. A lot of these experiments are operating sort of in a laboratory environment, and we need to get to a position whereby we can start to predict and understand how whole ecosystems are going to be affected. Because in essence, that's what we deal with from day to day. When we go into the field, we go to the ocean, go to the beach, we're not looking at one animal. We're looking at the whole environment, the whole ecosystem, which is full of complexities and interactions. And understanding those is a real challenge. But we started with experiments, and really that's where a lot of these new and emerging areas of research do start because they tell us an awful lot of useful information. And in Plymouth, we've run a lot of high CO2 experiments, ranging from very large experiments in these large tanks where we exposed organisms for a long period of time, to very small targeted experiments where these were actually looking at barnacle settlement under high CO2 conditions. And what we've seen is that as far as organisms go, the key thing to consider is the energy available to an animal to deal with stress. So if you think about ocean acidification as just another one of these environmental stresses that creates a greater energy demand on an organism, then you can see how it's starting to how all the effects that we see in our experiments start to fit together under this concept that actually it's about balancing the requirements of day-to-day life. So all organisms take in nutrients, they take in energy. Some of that energy is spent on just maintaining their physiology, so the daily running costs of the body. Then if you've got a little bit left over, you can then think about growth and reproduction and start to allocate energy up. So, one way we're starting to move away from just measuring endpoints and just looking at metabolic activity or respiration rates or growth is to bring this understanding in together, things like this. This is a dynamic energy budget model. And in fact, in essence, it's just a step forward from the scope for growth models that maybe some of you will be familiar with. But what we're looking at here is trying to conceptualize how all those different physiological trade-offs play out within the organisms itself. So food comes in and is stored into a central reserve, and from that reserve you then fuel the costs associated with living in a highly stressful environment, and then also making some ecological choices about reproduction and structure. And of course, the thing we need to understand about this kind of model as well is it's not static, as the name implies, dynamic. The fact is that organisms aren't necessarily going to be making the same allocation or choices of energy all the time, depending on whether they are going into a spring bloom situation where there's lots of food available might change the balance of the distribution of this energy. But in essence, what I want you to sort of take away is this idea that we need to start looking at the physiological endpoints we measure and try to conceptualize them into ways in which we can start to predict how organisms might be responding. Simple unifying theories that help us make that leap from a measurement in the lab to a prediction of how populations are likely to fare in the future. Another way of doing this, another modeling tool that we've been developing with our ocean acidification work is bioclimatic envelope modeling. And I spoke a little bit about this in the previous session, so I won't go into too much detail about this. But in essence, what it is, this is the model itself at the center of the network, and that's a representation of the model. The purpose of this model is to gather information from all different sources in order to be able to predict how likely it is for an organism to be able to survive in a particular area, knowing what that area will be like in the future, the environmental conditions that will be there in the future, and how that animal responds to those environmental conditions, and then scales it up to look at across the geographical range of that species. So again, it's about bringing information in from different sources. First of all, we have our scenarios, so predicting what the future will be like. We use ecosystem models to give us predictions of how the food availability might be like in that area. So looking at primary production in different parts of the distribution. Experimental data, looking at physiological response. How might the animals respond not just to the stressor itself, but some of the other environmental conditions we predicted, such as the temperature and food availability. We can't run all the experiments ourselves, so we then go out and get information from the literature. And also observations out in the shore, looking at current distribution patterns. But at the center of it all is this conceptual model that tries to bring diverse pieces of information together to make a prediction that's greater than the scale and scope of any of these individual elements. And what we see from models like this is really the column to look at, a combination of temperature and OA effects. This was a gastropod snail, which is common around the UK. And what we actually found was the model was able to predict that under two of the more likely scenarios for future CO2 emissions, large reductions in the abundance of these organisms in parts of their distribution. And actually, when you interrogated the model, a lot of that was driven not by the physiological responses of the animals to the CO2 and the temperature, but actually in the provision of the food that was likely to be available for them to maintain their energetic demands. So again, it's about understanding that not necessarily the direct impacts are going to be most important. Sometimes the indirect effects are going to be equally important. So before I sort of go into a forward-looking part of the talk, I'd like to just give you a few indicators of some of the key trends that we've found through a lot of this experimentation and modelling. First of all, if you're mindful to do high CO2 experiments, ocean acidification experiments, try to do them long term. Short-term responses are very good at looking at mechanisms, but we have found that organisms tend to switch those mechanisms based on whether they're trying to deal with a short-term response or whether they have to maintain that in the long run. It's a difference between a shock response and something that actually is settled in for the long run. We know ourselves that sometimes we deal with, if we know that it's going to be a short-term exposure to something, we might approach it in a very different way to if we have to deal with it year upon year. Impacts can affect species distributions within habitats. One study we did looked at a crab which lives in the intertidal, and we found that high CO2 actually affected its ability to recover from periods of being exposed. So the low tide periods when the animal was out was a bit stressful for it, but actually when the tide came back in, it was then able to recover. But exposure to high CO2 conditions meant that recovery was more difficult. So in essence, the ecological consequences of that will be that this animal will have to live further down the shore because it won't be able to survive a longer period of immersion as it could before. Then that has knock-on effects for the organisms that prey upon it and the organisms that it preys upon. It's changing the food web of parts of the shore. And as we've seen from the dynamic energy budgets, and we've also seen from the bioclimatic envelope modelling, we can get changes to species distributions across their ranges. And actually, populations are important. Just because you've done an experiment on one species, it doesn't mean you know everything about that species. Because depending on where you got your model animals from, your test animals from, they've been exposed to a very different history of environmental conditions than maybe a population that's a few hundred miles away. You need to be mindful that the organism that you're experimenting on is a product of the environment in which it's come from. So you need to understand that environment and know that's going to be different, and understand how different populations are likely to fare under what would in essence be the same conditions. Within species, priorities can change, and that's what we saw with the energy allocation. So depending on what the environmental conditions are or the time of the year is, whether it's in a season of lots of food or a reproductive season, or even if there's pathogens in the area causing another challenge. The idea that animals operate the same way at any single time throughout the year is wrong. Animals are a function of the seasonal cycle. Males and females respond differently to high CO2 in some of our experiments, and something that hasn't been reported. And again, why wouldn't that be the case given the different energy allocations that the genders go through at different times of the year? It would be hard to imagine situations where they would be responding in the same way. But sometimes that variability is missing from the data, is hidden within the data. So the net effect might be different if you pull the genders apart and look at them differently. And seasonality is a key process, as we've said. Look at the seasonal cycles. So when doing high CO2 experiments, it's very important to have good baselines, understand the natural cycles that you've got in your site before you then start to perturb them and move them away into a more stressful environment. And that, in essence, sort of encapsulates this idea of trophic interactions, competition, facilitation, symbiosis, infection. Organisms live in a world full of interactions. And high CO2 research is starting to move to an area where we're trying to understand these interactions on top of the direct effects. But a lot of the theories we've developed have come from these laboratory experiments, and we know that an organism lives in an environment that's far more complex than that. So how do we then start to test these theories, these lab-based theories, out in the real world? You can do that by bringing communities into the lab. We've tried in the past, or we have in the past brought in relatively natural communities. This is a nylon mesh here, and if you attach them to the shore, they get colonized by a community, and then you can bring that whole community in and start to manipulate it. And in fact, some of the things we've seen from those experiments have corroborated the theories developed from the single species experiments. The idea that we're reducing diversity in a whole community through high CO2, although actually it's more about reducing the numbers of individuals in these experiments rather than diversity. So we're seeing impacts across a lot of different species. And some of the different taxonomic groups were more sensitive than others, as might have been predicted due to their reliance on processes that involve calcification. So mollusks and arthropods were far more sensitive than annelids. And even within the mollusks, we saw big differences between the gastropods and the bivalves on how their sensitivity was affected. And by bringing communities in, we can start to deal with function. What is it these organisms actually do? So we looked at things like the calcification rate, the creation of calcium carbonate in the communities, and we saw a shift from a calcified to a non-calcified community as you increase the CO2 levels. But very interestingly, we actually saw the changes in that calcification, non-calcification shift, starting way before the saturation state of the water got to a state where the carbonate was being dissolved. Meaning that it's not just a dissolution problem, there is a physiological problem. And that fits in with this idea that it's about supplying energy to calcification. And even though you're not seeing dissolution of the shells, even a small change in the CO2 can actually make it harder to lay down the shell. Therefore, you're having to sacrifice energy from somewhere else, and in this case, it was growth. But again, mesocosms, they're not the real world, and many ecological processes can't be done in a mesocosm. So what other complementary tools are available to us? Well, there's a whole host of things to look at when you're doing ocean acidification research. And I don't think any of these are the perfect way to do high CO2 research, but what they do is each one of them tells us something new and something different from a different approach. So the key thing is to start to draw the information from each of these different approaches. A lot of laboratory experiments that we're very familiar with, but also field observations, looking at areas where CO2 is naturally highly variable, and having a look and seeing how the organisms cope and respond in those places. Some of you may have heard about these natural CO2 vents, where you get volcanic CO2 coming up through the seafloor and changing the pH of the oceans around them, almost like a natural laboratory. Laboratory mesocosms, something similar to what I've shown here. But one thing I'm going to talk a little bit about now is this FOCE. It might be new to you. Some of you may have heard of it. Free Ocean Carbon Enrichment Experiment, which we think is something that's developing and brings a novel perspective and aspect into high CO2 research. It was a concept that was developed by the Monterey Bay Research Aquarium in California, whereby a team of people looked at these experiments, the FACE experiments, the free atmospheric CO2 enrichment experiments. What you have here are big pillars built in the forest which pump CO2 gas into the center here and recreate a future world of high atmospheric CO2. And then scientists go in and measure all sorts of ecosystem functions and processes that are going on in these systems. So the guys at Mbari said, okay, well, why can't we do that in the ocean? That looks like a way of taking experiments from the laboratory and putting them out into a much more natural context. And the first thing they built looked very similar to those FACE experiments. So you had an area in here which was supposedly going to receive sort of high CO2 water. But they found that the dynamics of the marine system was far more complicated than the atmosphere, the terrestrial system, and actually this kind of approach didn't work. So they took a slightly different approach, which was more along the idea of these chambers, these flow-through chambers, almost like a flume, whereby you can start to manipulate the high CO2 water going in here, allowing it to flow over the system and then flowing away. So in essence, what you're doing is you're exposing a sort of a natural part of the community here to high CO2 conditions from the future. They've started to conceptualize what these FOCE systems are going to look like. So in essence, you have an area whereby you create this high CO2 seawater. You then pump it down to chambers on the seafloor and circulate it around and let it go to waste. The key things to remember are you need chambers whereby you recreate the experiment, the high CO2 future. You also need chambers where you just look at the effect of the chamber itself. There's a procedural control. And very importantly, linking into what I said about the variability of the system, you need to have reference areas so you know what the natural changes are likely to be going on alongside. They are very complicated to run at the moment, but they are being run. The first one was run on Heron Island in the Great Barrier Reef, and this is what's called coral prototype FOCE. And you can see the chambers here sat on the seabed in very shallow water here. In essence, the water would flow in, be mixed with CO2, and then flow over the system and away. Now, this was very much a prototype. It ran for just a few days to start with, and actually they brought corals in and put them in here. So it was a bit more like a mesocosm experiment in the field than future FOCE systems are likely to be. But they did manage to recreate an offset of CO2 from the natural environment that was in line with the kind of predictions we'll see with high CO2 future. The next people to try this were in Villefranche in the Mediterranean, and this was the EFOS, the European FOCE system. And this was an experiment run on a Posidonia meadow. Here you can see the big chambers with the diver in here sampling away. And they managed to run this system for much longer. They have an offset of 0.25 pH units, and here you can see the CO2 levels in the chamber as they started to bring the CO2 levels, the pH levels in the chamber, as they started to introduce the CO2. And the important thing, I think, from this diagram is to show the rhythm, the cycle in there. In essence, what you're able to do in these systems is have an offset from this natural rhythm of high CO2, which changes tidally. It can change day to day. So we're moving away from this idea of a static CO2 level to something that mimics what nature is really doing. We managed to take some samples from this experiment. We took macrofauna and myofauna samples from the sediment. And in fact, it's very early days with the preliminary results, but we found that there was very little impact on the macrofauna themselves. There were perhaps larger impacts on the myofauna, but in essence, a lot of the faunal component of this system was being buffered quite well in this environment. What we also saw was the microbial communities in these sediments was the area that most of the biggest impact was seen. And we saw a reduction in bacteria and archaea abundance after quite a short exposure to CO2. So if you think about why you might see that, well, maybe the macrofauna, it's not that they're not being affected by the high CO2, but there's plenty of food available for them in a highly organically rich area, and they can fuel the increased costs of this extra high CO2. But maybe they're going around there preying on the myofauna. So actually the change you see on the myofauna abundance might be due to predation and not any direct effect of the high CO2. And also with the microbes themselves, the myofauna themselves may be preying on the microbial element of the community. So what you're seeing is a cascade of trophic interactions which result in a change rather than any change in the direct sensitivity to high CO2. The very latest FOCE experiment that's been run was run by the Australian Antarctic Division down near their Casey station in O'Brien Bay, and this is the chamber itself on the seafloor. This here is the mixing tube where the CO2 is injected and it equilibrates with the seawater as it comes through and then flows out through the chamber. They managed to run these experiments for a few months. Here you can see the mixing chamber here. Incredibly long mixing chambers here because of the temperature of the seawater is very cold, so it takes a long time for the CO2 to equilibrate with the seawater and create the right kind of conditions. But in essence, again, they successfully deployed this piece of equipment, or this experimental design in a very challenging environment, so it's showing that it can be done. And these experiments in the field are starting to become doable, and I would encourage people, if this is something that really inspires you to have a go, don't be put off. They're complicated experiments, but they are starting to be achievable. And what the guys in Australia managed to get was a 0.3 of a pH offset for about 2 months to 8 weeks, And preliminary results from there shows that actually there were significant impacts on the macrofauna in this particular situation, and also there are impacts on some of the key ecosystem functions being conducted by the macrofauna, things like biotubation, sediment mixing rates. So with high CO2 work, ocean acidification work, there is no perfect experiment. There is nothing that you can go out and do that will fully replicate what ocean acidification is doing to our planet. We can't match the time scales, we can't match the spatial scales. What we need to do is to take a toolbox of approaches that each of the particular tool we use gives us a piece of the answer, and then start to put the pieces together in some kind of conceptual framework. So if you happen to do experiments, that's cool. What you need to do is understand the mechanisms that are being affected by CO2. Or you're looking at whole ecosystems themselves. That brings something else to the table. And I think FOCE, as a technology, actually bridges a gap between what we've been doing very well so far, which is the small-scale manipulative experiments and maybe the bigger observational type approaches at the vents and at the natural systems. FOCE brings something new. And it's particularly well suited for testing hypotheses. So if we have a conceptual understanding of what we think the high CO2 future might look like, we can then use FOCE to maybe challenge those hypotheses and test to see whether our predictions are right. And then when they prove not to be right, we can go round again and use this iterative cycle of trying to understand more to make much stronger predictions and predictions. So ocean acidification operates over temporal and spatial scales that make the perfect experiment impossible. But that shouldn't stop you from running experiments. You should just be mindful of what it is your experiment is designed to do. We need to understand the long-term impacts on individuals, populations, and ecosystems. And with that, we need this toolbox. We need a variety of approaches. We need to put together multidisciplinary teams in order to make those connections and those conceptual understandings. It's vital that we get teams to work together, and often communication between people not used to working together. And we need new approaches. These are some of the approaches we're using. FOCE is fairly new, but there may be even more new and innovative ways of generating new understanding and new data. So think about how to be creative with the kind of approaches you need for generating knowledge and understanding. But FOCE, I think, is a valuable tool, and whilst it's difficult at the moment to do these experiments, it will get easier, and I think it will open up to the ocean acidification community, and more people will be doing FOCE experiments in the future. So with that, I'll say thank you very much for listening, and I'm very happy to take some questions.
Steve, these are benthic examples. Are you able to say a few words about, could you say a few words about your impressions of the effect on phytoplankton or at least any planktonic organisms?
Yeah, absolutely. I mean, I sort of constrained myself to the benthic systems as that's the areas I work most in and I know most about. But there's been an enormous amount of work on pelagic systems looking at high CO2 impacts. In particular, phytoplankton, the idea of, CO2 is such a key nutrient for fueling the whole system that it became the obvious place to start, really, knowing that CO2 levels were changing, that phytoplankton might change. And there's been ranging from small experiments to very large pelagic mesocosms. People like Ulf Riebersell have pioneered the kind of sort of mesocosm experiments whereby they have these huge bags in the ocean where they seed CO2 in and follow natural phytoplankton blooms and see how that affects the system. And there are strong CO2 effects, and I think, but it's very taxon specific. The classic example of the coccolithophores, who, because of their reliance on calcification, seem to be the ones that are most likely to be affected. But I think also some of the other taxa, the diatoms and the dinoflagellates, are showing signs that they may be susceptible to CO2 changes. And it might not just be about changing the CO2 levels, but it might be changing the availability of other key nutrients as well. So changes in water pH might change iron availability, or it might change silica availability. So a lot of the things I've said for benthic communities hold true for pelagic. It's not just about understanding the direct effects on the organisms themselves, but all the key interactions, the trophic interactions, and how they interact and interplay with each other. But also, one thing that we didn't talk about was the connectivity between these two ecosystems as well. You know, the benthic pelagic coupling, the provision of nutrients from the sunlit surface oceans down to deep benthic communities. We need to start really considering ocean acidification at the kind of scales at which it's acting.
Thank you. When I was looking at the difference between the phase and FOCE.
Yes, yeah.
So two things struck me is that the size
Yep.
and the fact that terrestrial system was open.
Yep.
So then allowing immigration, which is extremely important, especially when species are facing a threat. And so then when I look at the system, the FOCE system, of course it's a lot smaller and it's closed. So
It's not closed.
oh, it's not closed.
No, it's not closed. No, the very first one, they were restricted, but they weren't closed. The idea is to have the natural seawater comes in at one end and gets inoculated by a high CO2 brine, a very rich CO2 sort of, not brine, but a high CO2 inoculum. And then it mixes and equates, and then it goes into the system. But it is natural seawater that's coming through. So you have that sort of input of larval material, of organics, of all that kind of thing. But you're completely right that the size is another issue. Scaling up to something as big as those phase systems would be an enormous challenge at the moment.
And so that's an enormous challenge.
Yeah.
So there's no easy way, I guess, to manipulate a larger area. Maybe with a system of holes, like a garden, you know, when you have holes on the ground, with even holes inside it. Then
I don't see a reason why these systems can't be built bigger, other than some of the engineering challenges and the deployment challenges. But we know, a lot of new approaches. They start from somewhere fairly small, and we soon see them expand. So what we're seeing now is a technology almost at the start of its journey with us. So I'm very hopeful that these kind of technologies will develop in ways that suit the kind of experiments we want to do. And that's where I think the developments need to be driven by. If we see that they're restricting us in our ability to make predictions in a certain way, we need to find a solution that enables us to expand them to do that. But it's an aspiration to get bigger.
I think you have touched upon the difficulty of maintaining an experiment for sufficiently long time to mimic an ocean acidification event or process. So at the same time, you showed some long time series data from various locations. Has anybody looked at changes in the ecosystem at those locations and been able to show that there are commensurate changes in the ecosystem at those locations?
Yeah, there's a few classic areas where we've been seeing rapid changes in CO2 conditions. There was a site in Tatoosh Island, which is an intertidal site that's been monitored on the west coast of the United States for a long time by a researcher called Tim Wooden and his colleagues. And they've been assessing the intertidal communities over many years and measuring the carbonate chemistry changes. And they've seen that despite a lot of noise in the seasonal cycle, there is a general trend for the CO2 levels at that site to be going up. And commensurate with that, they've actually seen shifts in the community where they've seen that the calcified species are being replaced by the non-calcified species. And it's not been happening that the calcified species all die and therefore the others come in. But what's happening is when organisms have been naturally dying off, the chances then of that space being recolonized has been greater for a non-calcified species than a calcified species. So it's restricting the recruitment into that area. So the change has been through calcified species dying as they normally would, and then a bias towards the new recruits coming in. So you see that the community is generally moving towards a non-calcified community. And that's actually a real example. And maybe it's, again, gives us an insight into how communities might start to change in certain areas. Okay.
Dr. Steve, thanks for your time and work. It's awesome. Nevertheless, I have a question. It seems to be that the efforts on doing bigger and longer experiments, it's leading this kind of work. Still, I have some concerns, and I would like to hear from you on the ethical side of pumping huge amounts of CO2 in cold water, such as the Antarctic ones. So I would like
the
to
ethics,
hear from
the
you
ethics, yeah.
what is the background of
Yeah.
this topic?
Okay. I mean, they did some calculations on how much CO2 they were actually putting into that area. And it paled into insignificance compared to the amount of CO2 that's going into those systems already. So whilst I understand that we need to be very mindful of what the impact we will have on experiments, and we don't want to lay waste to huge areas just to run an experiment, I think the nature of these types of experiments is actually once you run them, the impact is fairly small and localized, and the recovery afterwards is fairly rapid. I mean, compared to some of the things we do to our ecosystems, like demersal trawling, aggregate extraction, dumping and dredging materials, I think actually the impact of these things is fairly small. And of course, we are running the ultimate experiment at the moment with the amount of CO2 that we're putting into the system. So I do appreciate the concerns of being careful that we don't cause damage in our study, but I think I don't have too much of an ethical problem in this particular instance. Okay.
Just one thing. I used to spend the summers in the high Arctic in Canada. And if you look over the side of the ship there in the navigation season, the only thing you can see is pteropods. I wonder what the latest is
Yeah.
on the pteropods.
Well, the pteropods have become a kind of poster child for the ocean acidification research community because of their sensitivity to high CO2 conditions. For those who don't, pteropods are marine gastropods, pelagic marine gastropods that create beautiful shells, and they are fundamental parts of particularly polar ecosystems. And a lot of research has been done on these organisms, looking at their long-term future in a high CO2 world. And unfortunately, the sad news for pteropods is they exist in areas, the polar areas where cold water is taking up CO2 and changing far more rapidly than some of the warmer areas because CO2 dissolves much more readily in cold water. So they are facing the challenges of reduced carbonate saturation state in these areas, as well as the joint challenge of warming. The fact is that maybe they could move closer to the poles to flee from the global warming, the ocean's warming up. But of course, that's running straight into the areas that have got the highest amounts of ocean acidification. So I'm sad to say that pteropods could well be one of the first organisms that we lose. That's ended it on a really happy note.
Okay, if there are no more questions, I want to thank you very much, Steve, again for